I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm over at Rambus with Craig Hampel, who's going to talk today about cryogenic computing and cryogenic memory and what's new there. Craig, the idea of cryogenic computing has been around for quite a while. What is it and what's changed?
Well, cryogenic computing basically, and cryogenics in general, refers to a region of temperatures that relate to the boiling points of inert gases. And I guess technically anything below about 93 Kelvin would be considered cryogenic. With respect to computing, though, it gets interesting in potentially two or three different points. The first place it gets interesting is operating fairly conventional technologies, like based on CMOS, in that domain. For example, and a lot of interesting things happen. One of the bigger challenges in scaling CMOS has been leakage, and leakage really goes to zero really quickly and really reduces its ability to be a problem. And that affects things like DRAM refresh, and in many cases, the static power consumed by a circuit. And that really goes away in the entire cryogenic domain. The next place that it gets interesting and a major discontinuity in our ability to build computers and circuits is in the superconducting domain. So down around 4 Kelvin and for some materials as low as 7 Kelvin, you have these phenomenon where effectively the wires superconduct. And that does two really important things. It lets you signal over longer distances with extremely small amounts of energy. So the power consumption for those circuits approaches zero to communicate on wires. And the performance of those circuits also approaches that of an optical interconnect. The last place that cryogenic computing gets interesting is in the quantum domain. Most of the known approaches to achieve a qubit require extremely low thermal noise. The only place to get extremely low thermal noise is at extremely low temperatures. So some of these quantum machines are being targeted in the millikelvin range, which interestingly makes those systems the coldest place in the entire galaxy or in the universe. And that's a really interesting spot for cryogenics.
Why don't you draw this out for us? Give some visual here.
So if you take a look at kind of conventional memory subsystems in conventional temperatures, there's a fairly short list of useful memories in there. There's SRAM and DRAM. Certainly there's the solid state storage flash. There's also some emerging memories, PCM, phase change materials that could potentially have an impact here. Rambus is doing some work in RRAM. They operate up here, from 0 at 270 Kelvin up through 80 degrees C, which is 350 Kelvin. They operate there, and they achieve a known amount of power. Power scaling and power density is a significant problem. The power consumed by these circuits is not really going down very quickly anymore. Some of these, as you move these around in these kind of conventional temperature domains, DRAM has some interesting phenomenon in that its refresh power begins to decrease quickly. A rule of thumb is that it decreases by a factor of 2 every 10 degrees centigrade. So the refresh power consumed goes by half every time you would decrease it by 10 degrees. So DRAM power kind of starts to really go down quickly in these conventional temperatures. So you'll see a rapid increase in its energy efficiency in these temperature domains. SRAM less so. You can benefit from some of the reduction in leakage. Flash actually gets somewhat better, but not really better, more energy efficient. And even some technologies actually benefit from localized heating in order to create their state change. PCM actually needs to locally heat up elements in order to actually perform its right operation. So that's an unattractive characteristic of PCM for these cryogenic environments.
So when you're working with this stuff, what do you actually need to think about? This is a very, very low temperature type of device. You're dealing with a completely different set of dynamics than what you were on regular DRAM or any other type of memory.
Yeah, well, so what we think about is, okay, so if I then plot this conventional architecture kind of on a power versus temperature graph, I have to look at what memory technologies will best scale to these lower temperatures. being motivated by quantum machines and cryogenic computing or superconducting computing, which of these memory technologies, or potentially what new memory technologies might be interesting in these conventional domains. So the first thing you have to look about is, the first thing you ask, and when we started this project a little over a year and a half ago, we said, can I even make DRAM run at these low temperatures? The answer is yes. The next question is, can I make its power decrease be proportional to or better than the proportional increase in the cost of cooling? So that's the first thing you do, is you start to say, what circuits do I need to change to make this function? And then what circuits do I need to improve to get DRAM to significantly increase its power efficiency or improve its power efficiency at these lower temperatures? And the first place we kind of quantize that is at 77 Kelvin. And the two interesting things that provide a lot of advantage, the first one is that all the on-chip leakage decreases rapidly. So in some respects, a DRAM becomes a non-volatile device at this temperature. And then the second aspect is that transistor performance increases substantially, allowing us to decrease the threshold voltage at the same performance point and then decrease the resulting operating voltage of the device.
So do electrons move at the same speed at these temperatures? And so let me add that one question here. You're also talking about two different temperatures here. One is nitrogen, one is helium. What happens between those two?
Really, with respect to the wires and the transport delays of electrons, they really don't change very much in kind of between 77 Kelvin and conventional temperature. It's really more a transistor performance characteristic in the CMOS device that improves. When we get down to the superconducting domain, which depending on the materials might be 4 to 7 Kelvin are some ideal superconducting domains. There I get no energy loss in moving an electron, and the transport energy and transport time of an electron approaches the speed of light. It's not perfect, but it superconducts. That has some really interesting opportunities to do compute and memory subsystems down at these extremely low temperatures. And then secondly, even if I eventually do run computing operations down here in the 4 Kelvin domain, I still need high performance interfaces to take advantage of DRAM at maybe a slightly higher temperature. So there's a number of things needed there. There's new materials, new circuits, new architectures and design, and then also new interfaces.
So that allows you to develop DRAMs that are much more dense than what we have today, right? Because you're moving electrons much more freely.
There's two aspects of density. One of the greatest challenges in kind of what we call planar density for a DRAM is the size of the capacitor, which is the minimum size of the bit cell. The size of that capacitor is kind of driven by how much leakage, how much capacitance, how much charge it needs to store. We do believe that just in a planar sense, potentially it'll be easier to build high capacity, high density DRAMs at these lower temperatures. The second aspect of density, though, that potentially might even drive additional benefit is what we'll call the spatial density or three-dimensional density. The reason you can't stack DRAM on top of DRAM on top of DRAM on top of DRAM and build a DRAM in a cube is really dominated by its ability to perform thermal dissipation. As we get this significant increase in power efficiency, we can potentially build more 3D density DRAMs as well. And that has benefits economically, but also now the wires get shorter, the delays get shorter, you get a lot of additional benefits from being built spatially more dense computing systems.
Where do you see this playing out in terms of markets? Is this the kind of thing that's going to be in the home? Is it going to be in the enterprise?
I don't. I guess I don't see the costs of cryogenics and the difficulties in cooling systems to this extent being viable in kind of consumer products, or even IoT devices or such. So I think the initial place would be in the data center, and the data center has kind of two ways it could potentially intersect the data center. We do think that we'll see cryogenic computing happening, meaning people using superconducting technologies. One example is a technology called Josephson junctions that is a logic element that could show 4 or 5 orders of magnitude more efficiency than CMOS. That's the first place that this technology will be used. Potentially the second one is quantum machines are going to need a fairly conventional infrastructure to make them usable and programmable. So we consider the memory subsystem being part of that, and I think you'll need solutions like this to build kind of high volume, viable quantum computers.
But you don't have to reinvent the wheel to do this, right? That's the big key here.
You don't have to. I think there is going to be an opportunity to build unique, standalone, totally from scratch memory subsystems in quantum computing and in cryogenics. But trying to do that at economic scale and at density is really hard. So our approach is to take fairly conventional DRAM architectures and DRAM designs and DRAM process and optimize them for cryogenic operation. So kind of don't reinvent the wheel, but take advantage of the opportunity to use what we have more efficiently.
Computing has always been done in the enterprise in a fairly stable temperature environment. If it gets too warm, server makers say they don't guarantee the integrity of the data. When you're starting to deal with this kind of an operation where potentially you have people running around in thermal bunny suits, you're talking about a completely different type of operation. What happens if that gets too warm?
The first place that kind of consideration happens is purely in reliability. The thermal stress and the high voltages necessary to drive high VT devices at temperature is one of the reasons we don't have the kind of reliability that we want, and it's an impediment to the reliability of the data center. So we do think by moving down the energy curve and the thermal curve, we immediately get better system reliability. Secondarily, at least the things we're working on, if you're working in the cryogenic domain and superconducting, when you cross the superconducting domain, creates interesting challenges. So you certainly need to be aware of the discontinuity in your performance at that thermal disparity. At 77 Kelvin, there's really nothing magic. The operation of a DRAM at 93 Kelvin or 50 Kelvin really isn't that much different than 77 Kelvin. So we're not terribly concerned about kind of local heating phenomenon or deviations at the junction from the operating temperature of the device. So it kind of depends on where you are on this curve, but in general, it's not a major concern.
One of the other things that quantum computing brings is potentially much more security in the basic function of the data. It's harder to tap into this. It's a completely different architecture. What does it look like for the memory? Is that the same application there?
The approach we've taken so far with memory, it stores electrons in a fairly conventional way on a capacitor. So I don't think there's a fundamental benefit of kind of cryogenic computing. Maybe one that is just purely physical, though. As you pointed out, it is wrapped in an environment that is extremely cold, and will certainly have detection, and we know that if it was tampered with. So your ability to probe a sealed 77K DRAM is much, much more difficult than your ability to probe something in the data center. So I think it's more the environmental improvements that would make it secure than something fundamentally electrical.
So what does this deep freeze architecture look like? Can you draw it out for us?
Sure. I think we're going to see clearly humans and the machine interface and the data and the interface to the data center is going to happen at conventional temperatures. So you kind of have the user sitting up here. I don't think any of us are going to be cryogenic anytime soon, but at least I hope not. But the user sits here and the interfaces in the world, and probably networks and interfaces and UIs all sit up here. And then you're going to have a domain of operating of certain aspects of the system. And I think also storage probably sits up here as well, at least for the time being. Until we see significant benefit in the density and scale of storage, it sits up here at kind of conventional temperatures. We envision then a layer of infrastructure that's kind of the support infrastructure, network traffic, network support, NPUs potentially, FPGAs potentially, but where we're focusing is on the memory subsystem. So we see DRAM sitting at about 77 Kelvin, just because that's kind of a natural temperature. And that will then interface to computing elements, some CMOS and some on other technologies that take advantage of superconducting interconnect. And then will be at kind of less than 7 Kelvin. We'll start to see CPUs, GPUs, etc., TPUs, a number of conventional compute technologies. And these also serve as the interface for quantum accelerators. So we think we'll see quantum machines down here. There's a number of companies doing quantum in the millikelvin range. And that's kind of the way that we see the computer hierarchy playing out in a cryogenically optimized environment.
How real is this at this point? We've been hearing about quantum computing probably for the past 15, 20 years.
I think all of these technologies are in varying degrees of maturity. I think people have tested DRAM. We've been running DRAMs at 77 Kelvin for a little while to characterize them. So I think the memory subsystem is probably the most mature. There is an understanding, IBM's done work, other companies have done work in the past on superconducting processing. It still has a ways to go to have the same scale as CMOS, so there's a lot of work to be done there. Quantum, I'm not an expert. I'm not a quantum physicist, so understanding the physics of a quantum machine and how real they are probably is outside of my understanding. Todd Holmdahl, who's one of the GM at Microsoft for this project, was quoted recently though as saying some days he feels like it'll never happen with his lifetime, and some days he feels like it'll happen tomorrow. One thing that is going to happen as soon as we have reliable qubits, as an industry, we know how to scale in exponentials. So when someone gets 10 reliable qubits and then 100, the next increment is 1,000 and 2,000, and you can do some incredibly interesting things with 2,000 reliable qubits.
What's the lifespan of DRAM operating at cryogenic temperatures versus a standard DRAM today?
Good question. I think there's really two things that drive the lifespan of a DRAM. The first is just kind of Dennard scaling, meaning you can buy more DRAM at more energy efficiency 5 years later, and at some point just maintaining the power profile of that older DRAM isn't worth it. As scaling slows, that's going to happen less rapidly. But the other aspect of it is there is a thermal lifetime of a DRAM. There is energy and stress induced by writing to a DRAM and sensing a DRAM and all the voltages required for that. So from a reliability standpoint, we do think this is going to have significant improvements in the reliability of the operation of semiconductor devices at these temperatures, which should increase their life cycle.
You also can lower the voltage that the DRAM needs to operate at to make this more efficient, right?
We have to. The graph I showed earlier, you get a significant benefit just from refresh reduction, but you really need to start voltage scaling, and in order to do that, we need to lower the threshold voltage of the device and take advantage of its higher performance at lower temperature to then lower its operating voltages. And that's something we're working hard on and optimizing now.
That has a consequence in terms of the reliability of how long this memory lasts over time too, right?
Absolutely. There's two aspects of stress. There's gate stress, which is voltage induced, and then there's the thermal stress, which obviously is thermally induced. We believe we'll be able to decrease both of those.
And as the electrons are able to move more freely in and out of memory just because of the temperatures and far less power noise and things like that, does that knock down the stress on the system as well?
It does. Some aspects of a DRAM's reliability is what we call access induced or disturb induced. If we shrink the device, we still have to deal with some of those issues as well, although they are smaller at lower voltage. So there are still some considerations with respect to reliability, more caused by the activity on a device, less so because of thermal and voltage stress.
So why is Rambus interested in this? This seems to be a sort of a fairly far forward-looking technology.
Yeah, Rambus has always been interested in kind of leading-edge memory technologies and what platforms drive the adoption of new memory technologies. I think we went public 20 years ago yesterday, I believe. And the first platform that really drove the adoption of new memory technologies or disruptive memory technologies was the game console. Game consoles needed extremely high natural data type performance at low cost and at low power. So that's what really made the company was the memory requirements for game consoles. That later transitioned to the PC and digital televisions. But the really technology that drove that was the game console. More recently, certainly the PC hasn't been able to drive new memory technologies. Game consoles haven't. There's been some interesting innovations in low power in mobile devices. But the place we believe the opportunity to drive really significant disruptive memory architectures is in the data center. And frankly, there's no better company to work with than Microsoft, given their kind of advanced research and their strong presence in software as a service and the data center. So for us, it's a very natural evolution of that game console history.
Craig Hampel, thanks for a great look into the future.
You're welcome.